Exercise 98. Let's talk about the Rham representations. So remark. So we have introduced this FG regular rings, and also understand this category filter character space. Now we set F to be QP, and J to be the absolute Galois group GK, and we look at the Rham representations. So we have briefly mentioned the definition of the Rham representation. It is the representation that B Rham admissible. Recall that. So I would rather just recall that B Rham is a field, and it is QPJK regular. Remark. Now let's define a functor. D Rham applies on a representation. Any GK Galois representation defined to be B Rham tensor over QP basically, and then take fixed point. By what we have discussed in general last exercise, there is alpha way. Let's call it alpha Rham here, just to be able to read this information of which period we are working over from the index. So it tells us that if you first apply this dB way, so here means tensor is B Rham and takes a point fixed by JK. So this would be let's quickly recall what it is. B Rham fixed by JK. This should be K. Let me make sure. Yeah, so this is just over K, and then map to B Rham over QP, right? Let's recall the definition. P-adic representation way of JK is called Rham. If it is B Rham admissible, equivalently by our result of the last exercise. We give alternative definition of admissible by computing the dimension of the Rham is an isomorphism, or the dimension of d the Rham of V equals dimension of V as QP vector space. Important example. Take an integer n. Then notice that the Rham of this QPn is 1 in the dimension. Hence equal the dimension of the representation. So this is the Rham. So put this as a sub exercise. So actually this, what it is, this is be the Rham twist and then fixed by JK, right? And so this is the Rham. So this exercise asks you to compute this. It's claimed as K module. This is isomorphic to K. It's K vector space. So we don't have to describe the JK action there, but well, whatever. Anyway, this is trivial JK action there, okay? Moreover, there is a filtration structure on this K vector space, this filtered K vector space. It has unique filtration jump in degree minus n. In other words, graded piece minus n is non-zero. Because actually we should first define what is filtration, right? Let me describe. So let me put this remark 4 for a p-adic representation V of GK d the Rham of V is a finite dimensional filtered key vector space. With its filtration. Describe that for filtration. Field I, the Rham, way equals field I, beat the Rham. So filtration comes from this period ring part. This has a unique filtration because this is dimension 1, which means this should still be the Rham QPN, while field minus wait minus and plus 1 is 0. Yeah, this comes from the fact that how do we recall that? How do we define the filtration? So this really comes from the filtration I of beta Rham twist. Right? That's by our definition of this. So it gives this, so the filtration of beta Rham is clear, and then by that twist the filtration jumps, right? We have done this exercise before. I want to quickly check the filtration of beta Rham. How did I mention that before? So recall that phi I of beta Rham is defined to be beta Rham times t to the power I. It's also the that twist. Now we'll let this representation, the Rham QPJK, be the category of p-adic the Rham. Representations away. Okay, and then we have this functor. Actually, this image fall into filter vector space. Actually, I want to be more precise here. So how comes this filtration jump is let me put it as exercise. It has a unique filtration jump integral minus n. So how to describe that? Actually, so we want to look at this filtration here, right? So we know what is this. So field I, let's just compute it. So field minus n, the Rham of QPN would be just this is just equal to field minus n be the Rham, and then tensor with QPN, and so this would be just, and then fixed by JK, and then this wouldn't be just field minus n beta Rham twist n fixed by JK. I say what is this? When twist by n, yeah, it's described. So field I of beta Rham is when this is like beta Rham t to the power n, but field minus n means it times minus n. This is beta Rham fixed by JK, and so this is k. But as you could imagine, once you increase one, then what we left is beta Rham times t, and then the point fixed by JK should be 0 then. Right. Of course, this needs proof. This should use the facts from Tetson again, I guess. Because Tetson proved that for C, twist I, the point fixed by JK is 0. CK is isomorphic to the filtration beta Rham quotient by filtration. Okay, so second exercise, let's prove that. The Rham functor just constructed is exact, faithful, and the tensor functor to prove. Let's first prove the exactness. So notice that this functor, so this is a field, right? So this tensor is exact, there's no problem. So if you have exact sequence Rham representations, is it Rham representations. Then obviously you have the exact functor, and then you take the point fixed by JK, that is left exact, and so together it gives you left exactness. But then this is again a vector space, right? It's just K vector space, and it's to show the surjectivity enough to just count the dimension, but we know the dimension of they have the same dimension, so dimension V equals dimension V prime plus dimension with double prime. This implies the dimension of, because by the admissibility or by the definition of the Rham representation, this equal this and correspondingly, right? So you have and this is enough to conclude that this is surjective. So the exactness is okay. And it is faithful. I have to show that we have injective map into this. So this is again just both sides. This is just a homomorphism of vector spaces. So they're just linear transformations, right? So if you have a linear transformation here which is 0, then it means that either this is 0 or this is 0. construction. This will tell that, or by the fact that they have the same dimension, this will tell that this is 0, this is 0, and this will force f to be 0, right? Now let's check if, lastly, if we have V1, V2 to the Rham representation, then we have to check that with isomorphism. As, or in this category as filtered key vector spaces. So on the one hand, we have V1 injective into a tensor as vector space, because you can extend the vector space, just count the dimension. And this induces again as vector space. So this dimension are the same is really something very strong to talk about those things in filtered vector space of K. Respectively, this is in field of K. This is a K vector space, so both are free modules. Then we have this. We know that we could, in this particular case, we have the exercise for tensor product. This is again injective map. Again, you could just argue by dimension. So now, by last exercise, should be 97 if I'm correct. There must be the dimension of D the Rham with one tensor, D the Rham with two equals we know that this dimension is just the dimension of this times the dimension of this, and so it's the same as dimension V1 tensor V2. But then if you compare this with the Rham of this, then in general we know the question is we're talking about whether this is again the Rham representation, right? And so we're going to compute the dimension, compare the dimension. In general, this is smaller. Right, this is less equal than that. And so you see that you have something, a subvector space of this, but this has dimension less equal than that. And so this must be, right, this is telling you that the dimension of this should be less equal than the dimension of this. Or this is telling you the dimension of this is bigger or equal than the dimension of that. And so this must be an equality and so it is again admissible, and so this is again the Rham. Lastly, to check the due object. It's carried out by the functor, so we have the due. Suppose with the Rham, we look at the QP due. The question is the Rham we due is it isomorphic to the Rham and then due and filtered k-vector space. What we know is that the Rham with due is by definition the Rham tensor or QP with its home functor QP with QP x by jk, and by our results from tensor product, we know this is home B the Rham. This is just base change or scalar extension. And then jk. Recall you take element here, and the EX98 is mapping element x to j f j inverse of x, right? And then to be jk invariant, should be taking I mean this equals fx for whatever j and whatever x, right? Sub exercise. If this imply that, I mean, in general, let's say home AB J, this imply that home ABG equals home AJBG. Obviously this is contained there. Let me write home AJBG. This is contained here. The question is this equality? Home AJBG. And we claim that this is equal to home the Rham take fixed point on each part. The second part we know is k, but again Tesson. And so this is exactly the due of the Rham. So we are done. sub-exercise also corollary. So I do it in the next video. Take any Galois representation of GK. Take an integer. Then this Rham is preserved under theta twist. Give you some hint. Hint is the remark we just described here. This remark this remark 3 tells you that QBN is still QBN the Rham. QBN the Rham, and then tensor product of the Rham is the Rham, right? And that's it. So let me use the proof. So V of n is just isomorphic to V. Tensor is QPN, right? That's it. And on the other hand side, V is isomorphic to Vn and minus n, and this is just Vn tensor is Q minus QP, right? So if V is the Rham and this is known to be the Rham, this implies Vn is the Rham. Conversely, if Vn is the Rham, because this is the Rham, it implies V is the Rham. So we are done.